Hello, I'm Dr. David Kordowitz, and welcome to programming. Today we're going to talk about functions. Functions are a mean by which you can reuse your code over and over within your program or bring that same piece of code into new programs that you write. This is a method to not have to rewrite the same thing over and over and over again every time you need to use it. Let's begin. So the mantra when you're coding should always be work smarter, not harder. This is because there's always tricks and methods to be able to reuse code and to use different techniques to reduce the amount of code you need to write in total. So let's think about this for a second. If you could reuse the same code, say something like the quadratic equation or the Pythagorean theorem or averaging numbers, it would be a lot simpler than writing that code every time you need to use it. This is nice because we can basically write a block of code that we can keep calling over and over and over again. This is going to be one of the core tenets of programming as we move forward. So let's look at a function, and I want you to think for a moment about the type of function that you learned in, say, algebra or calculus, where we sort of say the idea that a function is y equals f of x. Now, in computer science, functions actually function quite similar to this. So if we think about it, we're going to have what we call a return value, which is what you get out of the function or the result of the function, and that's going to be our y. And we also have a list of parameters that we give to a function called x. In this case, in y equals f of x, f is the name of our function, and whatever happens to go on inside that function, if we put in the value of x, we will always get back the value of y. Now, when we talk about computer functions, we need to do what we call a prototype. And a prototype is exactly what you see above. So what a prototype is it tells us what parameters the function needs as well as what the return value are going to be. So if we look at the example down here of the Pythagorean theorem, we say that the result is going to be a double. This makes sense because in most cases you don't have whole length sides. We then call our Pythagorean theorem function Pythagorean, and it's going to take in two values that are both doubles, a and b, where a is going to be one side of the triangle and b is going to be the other side of the triangle. These are what we call formal parameters because they're declared here and they are formally what you put into the program. And it's important to note that we have a single return value, which is a double. So let's take a look at this function and how we can implement it. So we start with our function prototype at the top of the code. This always goes first because it tells the computer that you need access to that function in the remainder of your code. If you do not declare it at the top, then you will not have access to it till after you have declared it or defined it. Our function definition here down at the end basically is that the Pythagorean is going to be the square root of the sum of squares. Now, I've included math up top so that we can get square root and pow. On Arduino, that's not always necessary, but is sort of a functional way of doing things. We say that our result is going to be a double, and then we say result equals the square root of power of a to the second and b to the second, and then we return our result, which will be our answer. Now, for those of you who have programmed in C and C++ before, you may recognize the fact that I could have done this all in one line. Instead of declaring a result, I could have just said return square root of power a squared b squared, but I figured this would be a little clearer for those of you who are still learning this. Now, if we want to call this function and actually use it, we need to put something in our code to actually call it. So in this case, I want to take the parameters of 1 and 2 and plug them into our function. So now in the loop, I've declared a variable called result. Now, if you note, the curly braces around the loop and the curly braces amongst the Pythagorean do not meet with each other. They're not nested or anything like that. So the scope of the two result variables actually is different. So they won't interfere with each other. The result then, I'm saying, is equal to the Pythagorean theorem, which is our function, of 1 and 2, which are our two sides, a and b. We then have serial.println and the result. If I run this, it's going to compute it, and the value it should get is 2.2360 and a whole bunch of other numbers. But when I have my print line here, if you notice, I haven't put a length to the print line, so therefore it's going to give me 2 decimal places, and I'm going to end up with 2.24, which is exactly what happened when I wrote this on the Arduino. So another thing we need to discuss here is, well, let's say I write the quadratic equation. Well, with the quadratic equation, I can't exactly use this format because we only get one return value, and as we know, when we solve quadratic equations, we actually get 2 values as results, which are the 2 roots. This requires a slightly different approach. So what we've been talking about so far is what we call pass by value. In a pass by value type setup, you simply are giving a copy of the value of the variable to your function. So if we go back to the box example that we've discussed before, you're basically handing the person who's running the function the inside of the box, so the contents of the box, which is just a number, a value. However, you can't edit this because you don't actually have the box to change the number inside of. So this is what we call pass by value, where in pass by reference, we actually pass you the box, and you would take the number out of the box and you can do whatever you want. When you give me the box back, whatever you've done to it stays. So we need to sort of set our functions up deliberately if we want to do pass by reference. And this is using the ampersand character, which is also defined as reference. Now, it's important to note, those of you who know C out there, this differs between C and C++. The notation here is completely different for how you do it in C and C++. The C method will work in C++, but it is overkill. So for the Arduino, we're going to use this in the C++ type setup to reduce confusion. So let's take a look at some examples. For today's first example, we're going to look at reading data from the light sensor and then finding the average of 5 samples. So to do this, the first thing we need to do is determine where the light sensor is located. We can do this from our diagram, which we've seen many times before, and we can see that the light sensor up here is located on A8. So we're going to go ahead and do a pound define ls for light sensor to analog 8. So we now need to do our setup and our loop. So the first thing we need to do is we need to determine if there's anything we need to do in setup. What I'm going to do is go ahead and turn our serial output on with the serial begin 9600. I'm also going to add the while not serial. And what that again is going to do is it's going to prevent the program from running until we have a connection on the serial port. We need to declare a variable that's going to contain our averages. However, we're not quite there yet. So we're going to do this here in our loop as an array. So we're going to say int, and we're going to say it's an integer, and we're going to say samples, and we're going to make it 5 long. Now what we're going to do is we're going to have a for loop that's going to go ahead and sample. So we're going to say for int n equal 0, n less than 5, n plus plus. So this is basically going to build a for loop that is going to iterate by ones from 0 to 4. Now we simply need to do our reads. So we're going to say samples of n is going to equal analog read of our light sensor. Now what we need to do is create the function which is going to average these and display them to the screen. I'm going to go ahead and add a delay in here of something like 20 milliseconds, and that's to allow the computer or the Arduino time to stay timed correctly throughout the program. This isn't necessary, however, may be desirable depending on the type of program you're writing. So let's declare our function prototype for our average function. So we're going to do that up top here, and we're going to say our average is going to be most likely a double, and we're going to call it AVG. And what we want to take in here is we want to take in an integer, and we want to take in an integer that we're going to call our samples, SMP, and we want to tell it that it's going to be a array of 5. We're then going to tell it, just for fun, we're going to go ahead and take an int and tell it how many numbers we want to divide by. So this is going to be capital N. We then put our semicolon, and we can copy this back again. So we're going to copy this, and we're going to bring it down here below the end of our code and paste it. We now need to write our code for actually performing the average. So to perform an average, what we want to do is declare a variable called sum, and we're going to say it's int sum, and we want to start it out as equal to 0. The reason being is we're going to add the different values in the array to this. So then we're going to declare again a for loop. Now note, I have to redeclare my n because n goes out of scope at the end of the loop function. So here we're going to say n less than capital N. We're going to say n plus plus. Now what we want to do is we want to say sum plus equals, and we want to plus equals our SMP of n. So what that's going to do is it's going to cycle through all of our values, and then it's going to give us the sum. Now what we need to do is, in the last step, is say that our average, or return to get our average, is going to be double of sum divided by double of n, because that's how we compute an average. So now up in our program, we can call that average and say AVG of samples, and our number of samples is going to be 5. So now I can take this, and I can then take the return value is going to be a double. So say double AVRGE for our average, and I can say AVRGE equals this, and that will give us everything we need. AVRGE equals average. So now that average is going to be equal to what we want, and so now all we need to do is serial.println of AVRGE. So that should be our program. Now it may throw an error depending on the compiler that you're using and the version of the compiler you're using. Apparently it didn't, on the size of the array. That does happen. So let's go ahead and run this, and you can see I'm getting values, and I'm going to take this and move it under a bright light. Now I'm going to turn it and make it dark. So you can see that the average is keeping up. So now let's try to abstract this a little bit more. So what we're going to do is we're going to say that we're going to pound define NS, which is our number of samples. Right now it's 5. Let's change it to 10. And then this is just going to be, I'm just going to use, instead of putting a number of samples, I'm just going to leave square brackets. That tells it that it's an array of unknown size. Now what we want to do is, in our function, we're going to declare this array using capital N, or sorry, NS, and then we're going to change this from less than 5 to NS. And then when we feed into our function after we read this out, we're just going to change this from samples equals 5, comma 5 to NS. And so what this is going to allow us to do is we can change NS to whatever value we want, and we'll get that many numbers averaged. So let's try it. I'm going to recompile it and write it to hardware. Let's open our serial monitor, and now I have it in the bright light, and I bring it to dark. If you notice, everything's running a little slower. That's because we're averaging together 10 samples instead of before we were averaging together 5 samples. And in fact, I probably should have gotten rid of that 5. Let's try it with 100 samples and see what happens. So again, I'm going to compile. Now I want you to notice that everything runs slower. That's because we're getting a lot more samples than we were before and averaging them together. Not only is it actually slower running, it also takes a little more time for it to propagate changes in light. Okay, let's look at a second example. So this example, we're going to look at doing the quadratic formula so you can sort of see the structure of pass by reference. So what we want to look at is when we do quadratic equations, they take the general form of ax squared plus bx plus c. Now, a, b, and c can be positive or negative, and then generally we say equals 0. Okay, so what we need to do is we need to write a function that uses the quadratic formula to compute all of this, to get the solutions and the roots. So what we're going to do is let's declare our function and prototype it up here. The first thing is the return value doesn't really matter because we're going to use pass by reference to get the roots back. So often we do something like return an integer, but you could return a void if you wanted to check if you don't want to have an actual value. Now I'm using the integer here for the reason of checking if it's an imaginary value or a real value. So I can return different things depending on what the output is. Now it's important to note by doing this, the actual return value from our function has nothing to do with the actual results. So we'll show you this. So we have int, I'm going to call it quadratic or quad, and what we need to take in is we need an int or a double A, double B, double C. So those are our A, B, and C coefficients. Now what we need to do is get our roots. So I'm going to assume that our roots are double, so I'm going to go double, and then I put an ampersand for reference, and I want to do reference R1 for root 1, and double ampersand R2. Now, because I'm using C++ style, that ampersand is all I need to do to tell it's passed by reference. If this were in a C program, we would have to handle moving around stars and ampersands all over our program, which is a little more work, but isn't that bad. So we're going to take this and we're going to copy the prototype down. So what I need to do now is go ahead and write the code. So let's first of all look at what we need to do. The first thing we need to do is determine if it's imaginary. If it's imaginary, we need to check to see if the elements under the square root are negative, to see if it's imaginary. So we're going to do int, we're going to call that section USQ for under square root, and that is equal to, if you remember, it's going to be power of b to the second, so b squared minus 4 times a times c. So now, actually, that we want to be a double. I want to say if USQ is less than or equal to 0, then what do we want to do? Well, we're going to go ahead and we're going to say if it's less than or equal to 0. Actually, we can just say less than 0 because the square root of 0 is simply 0. So if it's less than 0, then what we want to do is set R1 equals, say, 0, R2 equals 0, and our return value, and then we're going to return -1, which is telling us that we have an error. Now what we need to do is the rest of our equations. So we're going to say R1 is equal to, so if you remember, it's minus b. The top is going to be minus b, plus or minus, so we're going to start with plus, the square root of our USQ, which is what's under the square root, then divided by 2 times a. Now our second root is going to be R2, and it's simply going to be equal to the same thing except minus the square root of what's under the square root, USQ. So now we want to return something to tell us that we succeeded. It has become customary in most languages to return 0 for success. So basically, if it's less than 0, it's error, and if it's greater than 0, it's not. So let's go ahead and we're going to use the setup here to do our calculations to reduce our overall amount of code, number of times we run. So let's start here with something really simple. Let's say A is 0, and we're going to say that bx plus c. So let's say A is 0, B is 1, C is 1. So that basically means x equals 1. So let's go ahead and do that. So we say, we're going to say double A equals 0, double B equals 1, double C equals 1. Now we need to declare R1 and R2. So we're going to just say double R1, comma R2. Since I'm not initializing them, I'll go ahead and use the shortcut so I don't have to have two doubles there. Now we're going to say if quad of A, comma B, comma C, comma R1, comma R2 is less than 0, we're going to serial dot println, and we're going to say imaginary. And then we're going to do an else. So if it's not imaginary, we're going to do a, we need curly braces. We're going to say serial.print. We're going to print the two roots. So we're going to do serial.print, and we're going to print R1. And then we're going to do serial.print, and we're going to do a tab. And then we're going to do a serial.print ln R2. So this will print out our roots when we're at that point. So we have here everything we need except for we haven't started the serial port yet. So serial.begin 9600 and serial.while not serial. Okay, let's try this. So push it out. I save my code. I push it out to hardware. And so I have NaN and infinity. And this is because the quadratic formula can't really handle it if A is equal to 0 because it's a divide by 0. So, okay, let's try it if it's x squared plus 1x plus 1. So we're going to run that. So now it's saying that it's an imaginary value because it's not actually possible. That is correct, actually, that it isn't possible. So let's take an equation that we know is possible and works. So we're going to take x squared plus 1x minus 6. In this case, we know that we have two roots. One is going to be at -3 and one is going to be at 2. So let's see if we get that. And we get 2 and -3. Now let's try something. So I'm going to move this section of code that's in the setup into our loop. So I'm going to take this section of code that contains calling the theorem into our loop. And what we're going to do now is instead of having, say, A or our C equal to -6, what we're going to do is we're going to start it at -6, and then each time through the loop, we're going to change it. Now, to do this, I have to move my variables into the global scope because I need them to be consistent across runs. So I'm going to do this up at the top, and now we have to make sure now that we say C++ at the beginning of each run. So we're going to start actually at the end of each run. So that's going to be in our loop, and we're going to say at the end of the run is C++, which is going to increment C. So C is going to go start at -6, then it's going to -5, 4, 3, 2, 1, and it's going to keep going up. So we can also add a trap in here if we want to, and we can say if C is greater than 6 while 1 semicolon. So what it's going to do is once we get over 6, it's going to trap the program and stop it from running. Okay, let's give this a shot. Sometimes the Arduino will complain about declaring variables with values outside in the global scope. But if you look here, it worked just fine. So we had 2 at -3, and then 1.79 and -2.79, and it keeps going until our C value gets to somewhere around 0, and then we get this, and everything else becomes imaginary. So you can see that I've reused the code that I wrote for the quadratic formula here 12 times in the same piece of code. Now in the next video, we're going to talk about libraries which allow us to use our code even more, that allow us to just import blocks of code without even having to edit them in the program or copy and paste or anything like that. So with that, I'd like to thank you for your time today and see you next time.